Hello. In this video, we are going to derive the pi orbitals of cyclopropenyl cation C₃H₃ plus 1. We draw the three-membered ring in the plane of the whiteboard, and we represent the relevant pz orbitals on each of the three carbon atoms. And imagine these are perpendicular to the whiteboard. Now we need to form a reducible representation for the pi system. So we want to see how many of the three pz orbitals stay put under each of the symmetry operations of the group. Under the identity, each of the three orbitals stays where it was, so we have a 3. Under the C₃ operation, P1 goes to P2, P2 goes to P3, P3 goes to P1, so that is 0. C₂, the C2 runs through each of the carbon atoms and bisects the opposite side. Now we notice that P1 becomes minus P3 because not only does it become P3, but we change the phase because the p orbital has two lobes of opposite phase. P3 becomes minus P1, P2 stays put, but P2 turns into minus P2. So the character for C2 is going to be a -1. It's minus because in the process of doing the C2 operation, we change the phase of one of the pz orbitals. For the σH, the horizontal mirror plane, P3 turns to minus P3, P1 turns into minus P1, and P2 turns into minus P2, so this is -3. For S3, remember, a improper rotation, S3 is a C3 followed by a σH. So as soon as we do the C3 part of the S3, P1 goes to P2, P2 goes to P3, P3 goes to P1. None of them stays put, so the character there is a 0. Now for sigma V, the vertical mirror, we can think of one of the vertical mirrors as, again, bisecting the triangle, and that takes P3 into P1, P1 into P3, and P2 into P2, so the character for sigma V here is a +1. Our next step is to reduce the reducible representation into a linear combination of irreducible representations in the point group D₃H, because that is the applicable point group. One thing to remind ourselves is that for each of the classes, there is, for example, for C3, there are 2 operations in the class. For C₂', there are 3 operations. Where there is no coefficient, we imagine that there is simply 1 operation in that class. So now we use our reduction formula for each of the irreducible representations in the point group. Our first irreducible representation is A1'. And remember that our first step is a fraction, 1 over the order of the group. The order of the group is the number of operations in the group. And we see here that the number of operations in the group is 12. Then we go through each of the classes and apply our reduction formula. Recall that the first factor is the number of operations in the group, which is 1 for E. The second character is the character from the reducible representation. We have the color-coded in purple there. And the third factor is the character from the irreducible representation A1', which is a +1. To expedite our work, we will omit any factors for the C3 class or the S3 class, since their characters in the reducible representation are 0, and if we multiply anything by 0, we get 0. So our next class to work with is the 3 C₂', so 3 operations in the group. The character from the reducible representation is a -1, and the character from the irreducible representation is a +1, so we have 1 there. Now for sigma H, the number of operations in the class is 1. The character from the reducible representation is a -3. And the character from the irreducible representation is a +1. Then our last set of factors involves sigma v. We have 3 operations in the class. The character from the reducible representation is a +1. And the character from the irreducible representation, a1 prime, is a +1. So we notice we have 3 minus 3 minus 3 plus 3, which is equal to 0. So there are no a1 primes in the reducible representation gamma pi. The next representation we want to examine is a2 prime. So again, we have our 1/12. And we notice that the first 2 factors in each of these terms will be identical for every single irreducible representation. So 1 times 3. And then the character from the irreducible representation a2 prime is also a +1. For C2 prime, 3 operations. The character from the reducible representation is a -1. And then the character from the irreducible representation is also a -1 here. For sigma h, 1 operation in the class. Character for the reducible representation is a -3. And the character from the irreducible representation is a +1. The last term involves sigma v, 3 operations. The character is a1 from the reducible representation. And then the character from the irreducible representation is a -1. So we have 3 plus 3 minus 3 minus 3, which is again equal to 0. The third irreducible representation in point group D₃H is E prime. Times 3. And then the character from the irreducible representation E prime is a +2. -1. The character for C2 prime is a 0. Then the character from the irreducible representation is a +2. So we have 6 plus 0 minus 6 plus 0, so we have 0 E primes in our reducible representation. Next, we have A1 double prime. Then the character from the irreducible representation is a +1. Character is a +1 here. Then the character is a -1. Again, the character is a -1. So we have 3, -3, +3, -3. So again, we have 0 of these. A 2 double prime. One. One plus 3 times -1. And then the character is a -1 here. The character is a -1. And then the character is a +1. So we have 3 plus 3 plus 3 plus 3, which is 12, 112. So we have 1 A2 double prime included in the gamma pi. Last but not least of the irreducible representations, we have E double prime, 112, 1 times 3 times 2 -1. The character for the irreducible representation is a 0 plus 1 times -3 times -2 for the character. And then the last term is 3 times 1 times 0. So we have 6 plus 6, 12, 1/12, so we have 1. So we're able to break down the reducible representation for the pi conjugated system into 1 A2 double prime and 1 E double prime. So since we started with 3 atomic orbitals, we end up with 3 molecular orbitals. A2 double prime counts as 1. E double prime, since it's doubly degenerate, counts as 2. To see what each of the molecular orbitals actually looks like, we need to construct a table. And in this table, we make a column for every single symmetry operation of the group, not just for each class. So since we have 2 C₃s, we have C3 and C3 squared. We have 3 different C2 primes. We have sigma H. We have our horizontal mirror. We have 2 S3s. And we have 3 sigma Vs. So now we use the projection operator method. We see what happens to a representative p orbital, P1, under each of the symmetry operations of the group. So under the identity, P1 just becomes P1. Under C3, P1 gets rotated to P2. Under C3 squared, P1 goes to P2 and then to P3. So next we have C2 prime. So this is a C2 axis that goes along, for example, along here. And in the process, P1 flips over. So P1 becomes minus P1. So next we can take this particular C2. P1 turns into minus P2 because notice that in the process of turning over the p orbital, we change its phase. So now it's minus P2. And then for the last, we have minus P3. If we do a horizontal mirror, P1 gets reflected into itself, but the positive phase gets changed into a negative phase, so that's minus P1. Similarly, now we have S3. We do a C3, so P1 goes to P2, but since it gets reflected through the horizontal mirror, it turns into minus P2. And similarly for S3 squared, P1 goes to P2, then to P3, it flips over, gets reflected in the mirror plane, so it turns into minus P3. And for the vertical mirrors, one of them would be here, for example. So since it's a vertical mirror, it reflects P1 into P1 and it doesn't change its phase. And we get the same process. This turns P1 into P2. And this one turns P1 into P3. So now we have the effect of each symmetry operation on P1. And our next step is to multiply through by the characters in the character table for the relevant orbitals. So we notice that we have A2 double prime. The character for E is a plus 1. The character for C3s is also a plus 1. The characters for the C2 is a minus 1. The character for sigma H is minus 1. The characters for S3 are minus 1. And the character for the sigma V's is plus 1. So we notice that in the process we get P1, P2 plus P3 plus P1, P2, P3 plus and so on. So this can be reduced down to is simply P1 plus P2 plus P3. So that is the A2 double prime pi molecular orbital for cyclopropenyl cation. We also have E double prime, and to see what those particular orbitals look like, we again need a row of our table where we write down the characters from the irreducible representation in the character table. The character for E is a plus 2. The characters for C3 are minus 1 and minus 1. For the C2 primes, the characters are 0. For sigma H, the character is a minus 2. The characters for the S3s are plus 1 and plus 1. The character for sigma V are 0, 0, and 0. And if we multiply each row, each character in the second row by the character in the first row, and reduce the lowest terms, we get 2p1 minus p2 minus p3 for our E double prime orbital. But we notice this is only one of a doubly degenerate pair, and we need to determine what the other member of the degenerate pair is. Again, we use a similar trick from the projection operator method, and we first perform a C3 operation on each of these terms. So 2p1, so p1 through a C3 operation becomes p2. So if we do a C3 operation on 2p1, it becomes plus 2p2. If we do a C3 on p2, it becomes p3. So if we do a C3 on minus p2, it becomes minus p3. And then for the minus p3, if we have p3 itself, C3 on p3 turns into p1. So a C3 on minus p3 becomes minus p1. Now we might suspect that this term in red is the other member of the doubly degenerate pair. But this is simply a relabeling of the orbital that we've already derived. But if we subtract the term in red from the term in black, we actually get the other member of the doubly degenerate pair as 3p1 minus 3p2, which we can reduce down to simply being p1 minus p2. Our final step is to sketch out what the molecular orbitals actually look like. So we know that we have an A2 double prime combination where we have P1 plus P2 plus P3. And the way that we represent this is since P1, P2, and P3 have all exactly the same sign, they're both all positive, that means that they're all in phase. So we notice in this particular combination that we have along the top positive phase, positive phase, positive phase, so that's bonding. Along the bottom we have negative phase, they're all the same phase, so that's an all bonding combination. So this will be our lowest energy pi molecular orbital. We also have the E double prime combination, one of which is we have 2p1 minus p2 minus p3. So since p1 is positive, that's reversed, these reversed here. So since it's positive phase, positive number, we have positive phase on top. Here we want to have the negative phase on top. That's a mistake there. And for P3 as well, since we have plus 2P1 minus 2P2 minus 2P3, we have positive, negative, negative phase. Also, the coefficient for P1 is 2, whereas the coefficients for P2 and P3 are minus 1, which tells us that this atomic orbital contributes twice as much as P2 and P3. So we notice that we have, along the top here, we have positive phase, negative phase, negative phase. So we have, along the molecule, along here we have a node. So we have one node for the E double prime. The other molecular orbital we have is P1 minus P2. And since they have make that more obvious that that's open. So here is our P1 minus P2 combination. And again, this one also has a node. So we notice that when we have doubly degenerate or triply degenerate orbitals, they will always have exactly the same number of nodes. If they don't have the same number of nodes, then they can't possibly be degenerate. So here we have the lowest energy orbital has no nodes, and the higher energy E double prime combination has exactly one node. Thank you very much for your attention. Have a good one.